get this ball rolling. All right, so thank you everybody for coming, and Jacopo for agreeing to give us a talk. Just as a brief background, Jacopo Ghiglieri is a staff scientist at SUBATECH. He completed his PhD in Munich in 2011, followed by postdoctoral appointments at McGill, Bern, and CERN. And we're delighted to have you here. And I imagine you are happy to take questions as they come during the talk.
Yes, absolutely.
Wonderful. So yeah, so Jacopo, one of the world experts on quark-gluon plasma. We're really delighted to have you here. Please take it away. Thank you.
Thank you. So today I will try to give you an introduction to heavy ion collisions and to thermalization in heavy ion collisions. And as this is the first of the two talks, and I've been asked for the first one to really be at undergraduate level, so I will strive to do that. But if there are some concepts that you feel of like flying over your head, just stop me and ask me, and I will try to explain more or better. So then I will have a rather longish introduction on what does it mean to have a plasma and a quark-gluon plasma, and based on the fundamental interactions as we know them. So let's start with that. So we know that there are at least 4 fundamental interactions or forces, if we want to keep kind of a more like sci-pop language. And these are gravity, electromagnetism, the weak interaction, and the strong interaction of weak force and strong force. So of course, will not say much about gravity. We know that gravity is a long-range interaction that's always attractive. And if we're looking at the world of atomic or subatomic physics, we can essentially forget about it. So that's what we will do for the rest of the talk. Then there's, of course, good old electromagnetism, which is also a long-range force, though in practice, matter tends to be electromagnetically neutral on very large distances. So that's more of a theoretical thing than an actual important thing on long distances. And of course, we know that it can be either attractive or repulsive, and that it's what keeps electrons and protons together in atoms and molecules. So it's also the basis of chemistry. Then there's the weak interaction, which in this picture that I'm making is kind of a bit of the outlier, because you can think of gravity keeping, I don't know, galaxies and solar systems and so on together, and electromagnetism keeping atoms and molecules together. And then we'll see the strong interaction keeping nuclei together. And the weak interaction isn't really responsible for any important bound states we can think of, but it's what, for instance, allows beta decays, so of the neutrons and of any other nuclei or particles that have this type of decay. So it's also what allows the formation of neutron stars. And it's also very important in our sun, because it's what allows protons to be converted into neutrons in the sun, so that they can take part in the rest of the nuclear reaction cycles that powers the sun. And it's a force that is extremely short ranges. So remember that the size of an atom is about 10 to the 10 meters. The size of a proton, as we shall see, is about 10 to the 15 meters. So this is much shorter distance than that. And then finally, there's the strong interaction, which will be what we will be concentrating on for the rest of the talk. So as I said before, that's what holds nuclei together. So it has a range that is the typical range of the size of an atomic nucleus, or well, that's actually the size of the proton. The atomic nucleus can be an order of magnitude larger, but at shorter scales than the size of the protons, we know that protons, neutrons, and all other states that experience the strong interaction. So for instance, an electron will not experience the strong force. If you put it close to a nucleus, it will only interact electromagnetically with the nucleus. But the particles that experience this strong force, they're called the hadrons. And in addition to the protons and the neutrons, there are many other more that are not stable. They're extremely short-lived. And all of these particles, we now know they are composite states of more elementary constituents, which we call quarks, and they're antiparticles, so antiquarks, and gluons. And it is these bags of quarks, antiquarks, and gluons, which we call hadrons, which are bound by the strong interaction. So it's something that we hear from well before we study them in detail in more specialized courses, that the protons and the neutrons are made of 3 quarks. That's kind of a bit of a misstatement. A better picture would be to say, so here I'm showing quarks in red, antiquarks in blue, and gluons in green. And again, what I'm about to say is also not super correct, but if you think about it at any given time, where this is a bit of an imprecise statement because there's relativity involved, but if you take a proton at any given time, it will have a lot of quarks and a lot of antiquarks, but there will be 3 more quarks than antiquarks. So that could be a proton, but this in the next slide where I've changed a bit the numbers of red and blue dots could also be a proton. And the modern view that unifies these 3 interactions, not gravity, is called the Standard Model. And these 2 interactions are then unified in what is called the electroweak interaction. This is not something that I plan to concentrate on in what follows. And the strong interaction within this modern view of the Standard Model is described by a theory which is called quantum chromodynamics, because it is based on the fact that there is, electromagnetism as the electromagnetic charge. Here there's a kind of more complicated version of that, which is called color charge. So chromo is Greek for color. And this interaction is so strong that it keeps quarks and gluons hadrons. So if you think of this as a quark and this as an antiquark, what I'm plotting here is the potential between this quark and antiquark as a function of distance in the limit where the quark and the antiquark are very heavy. So in red, I'm showing just what would be a standard Coulomb potential. So this type of Coulomb potential that we also know from electromagnetism. But what we see in QCD, in quantum chromodynamics, is more of this form. So you see that it looks a bit like Coulomb at short distances, but then it rises linearly. And of course, the force is minus the derivative of a potential. So we know that once we hit this range, the force stays constant. Whereas in electromagnetism, the force, which is still the derivative of the potential, goes down as the inverse of the distance squared. So that also means that in electromagnetism, or in gravity, which also has a Coulomb form for the potential, so I mean a 1/r potential, if I have a state that is at a distance here, so it has this much energy, and if I give it, the energy is negative, which means that if I want to free this bound state, I just need to give it this much energy to get it to 0 or above. Whereas if I am in QCD, I cannot separate this quark from this antiquark, because it will take me an infinite amount of energy. So that's the essence of what is called confinement. So that these quarks and gluons are the elementary constituents of protons and neutrons, but we will never be able to see in experiment an isolated quark or an isolated gluon, because they will always stick together in these bound states. I said always, and perhaps I shouldn't have, and that is what we will get into soon. So, because now let's discuss a bit in more detail the bound states of the different interactions. So if we consider electromagnetism, then the simplest bound state we can have is hydrogen, is the hydrogen atom. So I'm using now area of the circles as a proxy for mass, though in this case it's clearly not to scale, because otherwise you wouldn't be able to see the electron here. So we know that the proton has a mass of approximately 1 gigaelectron-volt over c squared, and the electron is about half an MeV. So there's this famous factor of about 2000 between them. And then what happens is that once they form a bound state, the hydrogen atom, if the bound state is in its ground state, we see that if we take the mass of the proton plus the mass of the electron, it's a bit more than the mass of the hydrogen atom. And this bit more is about 13 electron volt. So we went from something that is a mass of about 1 billion electron volt to something that still 1 billion electron volt, but smaller by 13 electron volt. So there's a very small difference compared to the total mass, which is called the binding energy. So that means that if you want to separate the electron from the proton, you need to give this much energy. And it's something that you can see in your undergraduate quantum mechanics, that this energy actually can be computed to a very good approximation from quantum mechanics, the Bohr levels, the Schrödinger equation, and so on. And you find that this number here corresponds to a very good approximation to just the mass of the electron times this fine structure constant squared over 2, where this fine structure constant squared, which is approximately 100 over 37, is the constant that the dimensionless constant that somehow sets the strength of the electromagnetic interaction. And also here, this bound state is non-relativistic, which means that the binding energy is really much smaller than the mass of any of the constituents of the system. And that is because, in this case, the interaction is weak. So this factor is much smaller than 1. It's weak in the sense that it's feeble, not that it's the weak interaction. Sorry.
So
but now, yes?
So to what extent is, could you ever have a strongly coupled system that's bound and is not relativistic?
A strongly coupled system that is bound and that is relativistic or not relativistic?
Not relativistic.
I suppose you could, yes. Like, definitely at least the excited state of quark-gluon are non-relativistic, but and strongly coupled. You could argue that the ground states, they are at least to some degree weakly coupled, but the excited states, they would definitely be strongly coupled. But they would still have binding energies that are, in particular in the case of bothonium, a fraction of the mass.
So how does that work? Because I think, here you really have a nice expression. E is m and then alpha squared over 2. So
yes.
If the only scale in the problem is the mass, then the binding energy has to be proportional to the mass. And the only way that would be small is if either, I guess, the coupling is small, or there's some huge, like 1 over some large numerical number that just comes out of the calculation. So,
well, at least in the case of QCD, you always have another scale, which is lambda QCD.
Right.
I don't know what would happen in a conformal strongly coupled theory. That, well, as soon as you put something massive, it will stop being conformal, but I don't know what happens in that case.
Okay, very good.
So then we have this hydrogen atom, and what happens if you heat, say, a gas of hydrogen? Well, what happens is that when you heat a gas, and we'll see more about that soon, each atom will have a typical equilibrium energy that is given by equipartition, which is of the order of the Boltzmann constant times the temperature. So that means that when the energy, the thermal energy of the atoms becomes of the order of the binding energy, and you allow for the fact that these atoms will be able to collide with each other, then there will be the possibility for the collisions to ionize the gas. And here I have the Fermi phase, which means that I'm doing a Fermi estimate, which means just an order of magnitude estimate. So you just take the scales of the problem and the constants, and you divide them to get an order of magnitude of the temperature when this will happen. So if you just divide the binding energy by the Boltzmann constant, you get a number that is of the order of 100,000 Kelvin. So you can think that if you can heat up a hydrogen gas to 100,000 Kelvin, you will be able to dissociate it. And the state of matter that you find when you dissociate protons and electrons is an electromagnetic plasma. So it's a state of matter that's electrically conductive because you have free electrons and also free protons. But in this case, it's really the electrons that are more important, a lot more important because they're much lighter. So that makes it electrically conductive and opaque to electromagnetic radiation, because now there's lots of free charges going on. So if you have electromagnetic waves going through something with lots of electromagnetic charges, the waves will naturally be absorbed, and you will have a system that's no longer transparent, but which becomes opaque. And such a state, of course, exists in nature because the cores of stars have a much higher temperature. So we said before 10 to the 5, this is 10 to the 7 Kelvin. And that's actually important for the stars to function, because at these high temperatures correspond to high kinetic energies. And that's what then will allow the nuclear reactions to take place and to overcome the electrostatic repulsion of the charged protons and deuterons and so on, all the other nuclei. So that's it for electromagnetic plasma. Now let's look at the bound state of the strong force. And the simplest one is, if we look at nuclei and not at hadrons, is of course deuterons. So the bound state of a proton and a neutron, which have approximately equal masses. And again, it turns out that if you look at the mass of the proton and the neutron, and if you look at the mass of the deuteron, there's a difference. And this time, the difference is about 2 mega electron volt. So before it was about 13 electron volt. So there's a factor of order 10 to the 5 in difference. So the bound state will still be non-relativistic, but now the binding energy is much larger, which is, in a nutshell, the reason why the density of nuclear energy, like nuclear reactors and so on, the density, the energetic density, so the energy per kilogram or per unit mass of your fuel, for a nuclear fuel is so much higher than for a chemical fuel like burning gas or oil or whatever. And so that means that if I do the same thing as before, because of this factor of 10 to the 5, I will need a temperature of the order of 10 to the 10 Kelvin to dissociate atomic nuclei. And that doesn't happen in the sun, for instance. And then I can take things one step further and look about nucleons. So as I said, these are the masses. And actually, here things change, because before I was always looking at bound states where you have very massive constituents, and the mass of the bound state is just a bit smaller than the mass of the constituents. This is very different now if we look at the proton, for instance. So, well, there is also a theoretical problem, because as we said, there's confinement. So the concept of a quark mass itself is ambiguous, because it's not something that we can observe differently from like the proton or the electron, where we have very good experimental techniques to measure their masses. We don't have an experimental technique to measure the mass of a quark, because we cannot ever observe a quark or a gluon. So we can define on the theoretical side what could be a mass for these objects, and there can be different definitions. But in general, these definitions tend to give rise to a proton, which emerges with its mass from constituents that are much lighter than the mass. So the proton has a mass of the order of the GeV, and the quarks have masses that are of the order of the MeV. So that means that it's something completely different, because its mass doesn't come from just the mass of the constituents minus a small binding energy. In this case, the mass comes almost entirely from the dynamics of the strong interaction. And the dynamics of this strong interaction somehow brings with itself its own intrinsic scale. So that's why, which is of the order of 2000 mega electron volt. Indeed, you never see hadrons that are lighter than this scale. The lighter hadron is called the pion, and it has a mass that it's about 140 mega electron volt. And on the theory side, so of course, in nature, the proton has the mass it has, and it has to come out from however we define the masses of the quarks. But in theory, we can play with pretend nature and like do Gedanken worlds, and we can think of a world where the quarks are exactly massive, and it turns out, exactly massless. And it turns out that in this pretend world, which is not the world we live in or the universe we live in, the protons would only lose 10% of its mass. So really the mass of the proton really comes just from the relativistic and intrinsic dynamics of the interaction. So it's a very different system from hydrogen or even from the deuteron. But however, the fact that the strong interaction has this scale means that if we could now heat strongly interacting matter to this temperature, so we've gained another factor of 100 from before. So before we were at 10 to the 10 with 2 MeV. Now at 200 MeV, we must be at 10 to the 12 Kelvin. So if we could heat up strongly interacting matter to this temperature, then we could dissociate hadrons into a deconfined quark-gluon plasma. So you are now having so many hadrons together that it's now each individual constituent isn't anymore confined within a single hadron. And that is what would be called a quark-gluon plasma. And before I explain how we can do that in experiment, let me just say a bit more about theory. So without explaining in detail what goes into producing this plot, let's say it is based on solving this theory of the strong interaction on a computer and looking at these quantities, which are the energy density per unit temperature cubed, and I will explain that in the next slide, the pressure and the entropy density. And you see that all these quantities have a sharp rise at a temperature that is about really a little less than 200 MeVs. So we know that at a temperature or Boltzmann constant times the temperature of the order of 150 MeV, there's this sharp rise in these quantities, which suggest indeed a change to a different state of matter. And now let me now discuss what these quantities mean. So I'm now showing just the right-hand side of this plot for illustration purposes. And let's look at the blue curve, which is the energy density. So what is the energy density? It's just the internal energy per unit volume. And in the non-interacting limit, if you have ultra-relativistic degrees of freedom, that's essentially given by the Stefan-Boltzmann law. If you're familiar with it, it's the law that gives you the energy density, for instance, of a black body as a function of the temperature, and that is proportional to the fourth power of the temperature times the appropriate power of the Boltzmann constant, of the other constants. And then there's this quantity here, which is proportional to the number of ultra-relativistic degrees of freedom. So in the Boltzmann, in the Stefan Boltzmann case for a black body, that they are just photons. So I think here you should put 2. For a QGP, this number is larger, but if you put the actual number and you input this temperature and all the constants, you find that this quantity here at this specific temperature becomes this number here. So you find that this would be this point here, and the actual calculation is a bit below, but we only care about the order of magnitude here. So this calculation is telling us that the quark-gluon plasma at a temperature of 400 MeVs should have an energy density of about 8 times 10 to the 36 joule per cubic meters. That looks like a very big number, but maybe it's only big because we're using stupid units. So let's compare it with something we know very well, like liquid water. So what's the energy density of liquid water? Liquid water is, to an extremely good approximation, non-relativistic. So the energy density is just essentially the mass density times c squared over the volume. So it's the mass density times the speed of light squared. So for water, the mass density is 1,000 kilograms per cubic meter, and then you add in a factor of c squared, and c squared is big in SI units. So for water, you would get something that is also big, but still, for the QGP, you get something that 17 orders of magnitude bigger. So in both cases, using SI units is not the best of ideas, because you don't want to work in units when even something that you're very used with, like water, has these very large energy densities. But still, that shows you that the QGP is very different in terms of energy density from something we're very familiar, like water. So then what would be your heating tool here? How can you heat up something and get energy densities that are 17 orders of magnitude larger than that of liquid water? Well, it turns out that you can do so by colliding heavy nuclei at large energies, and that also characterized the phase of the early universe. I will not discuss the early universe further, but let's concentrate on heavy ions, because we now have evidence from many different observables that a short-lived QGP can be formed in heavy ion collision experiments. So what do you do in these experiments? You have accelerators such as the relativistic heavy ion collider at Brookhaven in the US and at CERN between France and Switzerland. And you have two beams of heavy nuclei that are going in the two directions. Heavy nuclei means that they have a mass number of about 200. So it's lead at the LHC, and it's, well, when they want to do the largest possible collision at RIC, they use gold, although they also used uranium recently. And each of the beams is accelerated, well, in the frame of the lab to 100 GeV per nucleon at RIC and 2.5 TeVs at CERN. So what happens when you collide them? So here now I'm looking at the two nuclei. So one is coming this way, one is coming the other way, and I'm looking at them in the rest frame of the detector, so the so-called laboratory rest frame. So if I look at the nucleus in its own rest frame, most nuclei will look spherical. Some of them are not exactly spherical, they are deformed, but most of them are kind of spherical. However, if I accelerate them and if I look at them in a frame where I am at rest and they have a large velocity, then they will look contracted. That is the Lorentz contraction of special relativity. So in the lab frame, they look like these thin pancakes. And the gamma factor is what tells you how much they're contracted. So at RIC, it's about a factor of 100, and at the LHC is about a factor of 200, because it's essentially the ratio of the mass, of the energy over the rest mass. So the rest mass of each nucleon is about 1 gigaelectron volt. So that's what gives you these gamma factors. So then you have them collide. So what is the energy density when they collide? Well, let's just do some very simple geometry. So at the numerator, you have the mass and the mass density. So you have 200 times 2, so 400 times the proton mass times c squared. And what's the denominator? So the volume. So you have the surface of the cross-section of these nuclei, the geometric cross-section of these nuclei. And then for the third dimension, you have again the radius, but contracted, so divided by this gamma Lorentz factor. And if you do the math, it turns out that you get something that is in the ballpark of what came out from the theory calculation on the energy density of the QGP. So that tells you that you can get the right energy density. And that would be the focus of the rest of the talk. There can be the rapid formation of a medium that will almost look like a quark-gluon plasma in thermal equilibrium, which will live for a short time. So a time of the order of 10 femtometers over the speed of light. So again, the 10 femtometers was more or less the transverse size of the colliding nucleus, and c is the speed of light. And then this thermal medium will rapidly be expanding, and like any gas that expands, it also cools down until at some point it will reach again the temperature below which the quark-gluon plasma cannot exist, and you will form again hadrons that will then reach the detectors, or the decay products will reach the detectors, and they will be measured. I will discuss the experiments in a second, but now I want to see if you caught a bit of something that I didn't say here. So a possible flaw in the argument. So I said that you have this simple enough formula, you plug in the right numbers, and you get the expected, the energy density you want to reach. But that must be at best a necessary condition for the formation of quark-gluon plasma. So let's say, for instance, I look, instead of colliding two nuclei, I just have one beam. So if in the lab frame, I look at this accelerated beam of nucleus, I just divide this by 2, and it seems I also have, well, I divide the number by 2, but it's still in that ballpark. So that this means that one accelerated nucleus is a quark-gluon plasma. That wouldn't make sense, because if I move to its rest frame, then the energy density is just 200 mp c squared, and I lose the factor of gamma here. So it drops by a factor of gamma, well, of 1 over gamma. So that can be the whole story. So of course, I need the two of them for the energy to be concentrated in an interaction point. But then I also need interactions that can stop this energy at the collision point and convert this energy. So that means converting the nuclei or pieces of the nuclei into a quark-gluon plasma. Because even if I could accelerate the two nuclei, and then if again I do one of my Gedanken things, and at that moment I switch off the interactions, so they would just fly through each other and nothing will happen. So there needs to be interactions that can create the quark-gluon plasma. And that would be what I will concentrate on for the following. And this process in which you have an initial state that is a nuclear state that rapidly converts into something that is a quark-gluon plasma almost in thermal equilibrium is the process of thermalization, and will be what I will be trying to illustrate in this talk and in the following talk next Friday. And now, before I do that, let me tell you a bit. Oh, sorry, no, I forgot. There's still one more slide about theory, and then I will show you a bit about the experiment before jumping again into theory. So I wanted to say something about interactions and thermalization to maybe follow a story that you should be familiar with, and then try to explain why we do something a bit more advanced than that. So the thermal system that everybody knows about is the ideal gas. So the ideal gas is a gas of non-interacting point particles which obeys the ideal gas law. So for instance, for a non-relativistic monoatomic gas, the pressure is proportional to the temperature times the Boltzmann constant times the number density of constituents, and the energy density the same, except there's a factor of 3/2. However, again, this is a bit of a Gedanken gas because it is non-interacting. So without interactions, it can only exist if it has been magically prepared into a state. So if some kind of devil went and gave each atom the right energy, and then it stays in this state. That is not what we want here, because we want an interacting system that will start outside of thermal equilibrium. But in general, thermal equilibrium tends to be the state with the highest entropy. So evolution of isolated systems will tend to go towards thermal equilibrium because it is the state with the highest entropy. And what we will see is how this happens microscopically, with the question of answering how fast this happens. And now I motivate why knowing how fast this happens is important for the quark-gluon plasma. Because in the end, what your experiments see can be something like that. So this is from the ALICE detector. This is just one event. The ALICE detector has this detector. Well, a big part of the ALICE detector is this detector called time projection chamber, which can essentially image in 3 dimensions the tracks of all charged particles that go through it. And this was an event about 13 years ago at an energy that is half of the energy that I've been discussing so far. And you see that there are lots of tracks. So each of these lines is the track that a charged particle has made into the detector after a collision took place. And if you collect a lot of events, then you can do statistics, and it turns out that the number of charged particles per unit rapidity at mid rapidity, which means essentially, so here the beams are coming this way, and mid rapidity is this region here where they're going neither too far in the direction of the incoming beam or the other incoming beam, but they're rather coming orthogonally to the beam direction and then distributed azimutally. And if you count them in that slice of the phase space, it turns out that you have about 2,000 particles per rapidity unit, which is a logarithmic unit of angle, essentially. So the bottom line is that you have lots of particles. And how do you characterize the medium properties from measuring lots and lots of particles? Well, you can do essentially two things. Well, you can do many things, but they fall into essentially 2 categories. So you look at observables that tell you how the bulk properties, so you measure a lot of these particles that don't have a very large energy, and those are related to how the expanding fireball of quark-gluon plasma evolved, and how this evolution in general was described by hydrodynamics. And on the other hand, you take a complementary direction. So you look at the few particles that instead have a very high energy and that were not in equilibrium with the medium. So for instance, jets or electromagnetic radiation. And here I will briefly show one example, which is in the bulk category. So this comes essentially from, again, taking your detector, measuring all of these particles at low momenta in particular. And these are histograms as a function of the azimuthal angle. So here the beam is going through the slide, essentially, and then you're producing particles that are going out in all directions. And you're just doing a histogram of how many particles you have per each beam in the azimuthal angle. And you see by eye that this distribution is not symmetrical. So there are more particles in this direction than there are in this direction for this specific event. For this other event, there are more particles in this direction. For this other event, there are more particles in this direction. And this is called azimuthal anisotropies, and there can be different explanations for what drives it. But there's a sort of agreement that for the systems that have the largest sizes, so for like nucleus-nucleus collision, this is mostly explained by hydrodynamics, whereas there could be different explanations for systems that are called small systems. So you can also see this effect with a smaller magnitude in proton-proton collisions when you look for the proton-proton collisions that produce the most particles. But let's stick to heavy ion collisions. And then if you want to try to understand why you have that effect, you can think that, of course, heavy ion, the 2 nuclei, so the beam here is again going through the slide. And there's no particular reason why the two nuclei should collide perfectly head-on. In most cases, they would collide with some finite impact parameter, which means that the overlap region will be kind of almond-shaped here. So it's not azimutally symmetric, it's a bit elliptical, so it looks like that in position space. And if you produce a medium that is kind of a fluid so that it responds to gradients in pressure, so something that has this shape here will have pressure gradients, and your medium will respond to these pressure gradients and will convert this initial anisotropy in position space to a finite anisotropy in momentum space. And this is then the histograms we showed before. And this we can do in theory by describing the medium with hydrodynamics. However, it turns out that, of course, hydrodynamics give you equations that depend on time, and you integrate them over time and then match them to experimental data. But you can't start hydrodynamics right at the moment where the two nuclei go to each other. If you do, it turns out you don't have a good description of data. You have to wait a bit. So for instance, here you see in the black are the measurements of essentially an observable that is related to these anisotropies. And the colored points are theory calculations. And you see that, so for instance, the squares have, for the two observable V2 and V3, have this initialization time of 0.2 Fermi, which means that the hydrodynamic descriptions only starts after this small fraction of a Fermi. And in this other case, it starts with double that. And you see that the theory calculation then is sensitive to this quantity. So if you start hydrodynamics later, you underpredict, in this case, the data. And probably if you started it earlier, you would overpredict the data. And here the horizontal axis is something, again, that measures the number of particles produced by the collision. So this shows you that an interplay of data and experiment is telling us that hydrodynamics, which requires the existence of a fluid that is close to thermal equilibrium, is applicable after a short time after the collision. This time is not 0, and it's also not 10 Fermi over C, which is probably the duration of the whole lifetime of the quark-gluon plasma. So it takes a short but non-zero fraction of time before the interaction can turn the initial nuclear state into something that looks like a near-thermal quark-gluon plasma. So the question we theorists, well, at least people have been trying to answer is how? And how does this happen microscopically? And can we get a calculation that gives us a number that is in this ballpark? And so in the following, I will try to explain how you can do that. And there are many, the approaches, the theory approaches to the quark-gluon plasma tend to fall into one of these three categories. There could be others that I'm forgetting, and in this case, do let me know. So the one that is based on treating quantum chromodynamics, so the theory of the strong interaction, which is a theory that's extremely difficult to solve. So in the perturbative approach, you treat it by assuming that there is a quantity alpha strong, which is the QCD equivalent of this alpha, the fine structure constant. So for electromagnetism, this fine structure constant is a very small number, it's smaller than 100. So you can treat it as an expansion parameter and do what is called perturbation theory. So perturbation theory is something that in physics, I think, dates back to the 18th century when people were doing, I think, orbital mechanics, and they realized that if you have maybe the sun and a big planet, and then there's a third smaller planet, you can, and you want to know how the third smaller planet influences the orbit of the big planet, you don't need to solve the three-body problem, which is notoriously impossible to solve, or at least nobody has solved it analytically. I don't know if it's impossible, but it's certainly unsolved yet. But if you treat the third planet as a perturbation, so you expand in the ratio of the mass of the small planet over the mass of the large planet, then you can get something that is a lot more tractable, and you can get terms that go to higher and higher orders in the ratio of the masses. And here you try to do something similar to quantum chromodynamics. But the challenge here is that this expansion parameter might be of order 0.3 or even larger, so that expansion might not be very convergent. Then there is another method where you try to solve the equations of QCD directly, but these equations are essentially infinitely dimensional. So instead of solving this infinitely dimensional set of equations, you discretize your space-time, and you go from having an infinitely dimensional set of equations to have a large set of equations, which you can solve on a computer. But in this case, the challenge is that on the computer, you cannot use real time, but only Euclidean time. And for something like thermalisation, where time is of the utmost importance, at the moment, we don't have a way to really do this with this system for full QCD. Or you can give up on QCD and look at related but different theories, which have a so-called gravity dual, which is relatively easy to solve in the limit of strong couplings. And then here the challenge is to extrapolate from these different theories to QCD. So now I will concentrate on the theory approach that is based on the perturbative regime, so what I will call the weakly coupled regime. And then the picture is that the plasma is essentially constituted by particles, a plasma in equilibrium at least. Before it reaches equilibrium, it will be different, but it will be constituted by particles, quarks or gluons that carry an energy and a momentum that are of the order of the temperature. Before they reach equilibrium, they will carry an energy and momentum that are not the temperature, which is defined down in equilibrium, but that is the typical hard scale that becomes the temperature once you are in equilibrium. So the pressure and the energy density of the quark-gluon plasma will be, to a first approximation, be attributed to these particles. And in a perturbative setup, then in the first approximation, these particles are, if they are ultrarelativistic, they follow the Fermi-Dirac or Bose-Einstein distribution with massless kinematics. And then in the first approximation, if you neglect interactions altogether, the energy density, for instance, is obtained by this simple integral. So this is the term that these are gluons, and these are quarks and anti-quarks. So this 2dA is 16 because there are 16 gluons in the sense that they have two polarization states, just like photons, and then 8 color states. And these are quarks, which have 2 spin states times 2 antiparticle states times 3 color states times the number of quarks. So, up, down, strange, and so on. And by just doing this integral, you get this number that I was quoting above, that I was quoting before for the energy density. Here I've now moved to theorist units, because as I said before, it's a bit weird to use SI units where things have 8 to the 36 or whatever joules per cubic meter, or what was it? It's better to use units where the Boltzmann constant is 1, the speed of light is 1, the Planck constant or the reduced Planck constant is 1, and then you only have this proportionality to t to the 4th. And that is the derivation of what I've shown before. So that would be the thermodynamics in the absence of interactions. So that is, again, in this Gedanken system. But now we don't want the Gedanken system because, as we said before, if there are no interactions, the two nuclei will just fly through each other and no QGP will be produced. So let's look at what interactions do in the case of the pressure. So This is again, the pressure as before. It's a plot like the one I showed before. Again, in this case, the pressure is divided by the pressure of the ideal quark-gluon plasma. And you see it's always a bit below the pressure of the ideal system. And then as soon as you get to about 200 megaelectron volt, it becomes completely different from the pressure of an ideal quark-gluon plasma, because at this point there has been a transition to hadrons. And so the points here are the results from the lattice, so the numerical discretization of quantum chromodynamics, and the bands are the weak coupling results based on this perturbative expansion. So this is for thermodynamics. And now we want to do something similar for describing the dynamics. So how the interactions can take us from a system that is not in equilibrium to one that is in equilibrium. And that happens through kinetic theory. So the idea here is that we want to track the evolution of the phase space density of the system. So the number at any given time, we want to follow the number of particles per unit momentum and per unit volume. And in equilibrium, this becomes precisely the Bose-Einstein or Fermi-Dirac distribution. So here the question is, how does F, which will start from some state that is not thermal equilibrium, evolve towards thermal equilibrium? And in kinetic theory, which is what is appropriate for equilibration of weakly coupled systems, so systems which have a small expansion parameter and you can do perturbation theory, this happens through a Boltzmann equation. So the total time derivative of this distribution function equals interactions. Now I will get in a second to what the right-hand side actually means and what is the fine print for this equation. So when does it apply and when it doesn't? Of course, with a bit of classical mechanics, you can rewrite the total derivative as a set of partial derivatives. So there's the partial derivative. Then there's a term which is the velocity. So if your fluid has a velocity, that multiplies the gradient in the spatial variables. And dp of dt is a force. So if there's an external force, then there will be also a term that multiplies the gradient in momentum. And so what are the interactions? So for weakly couples, oh, sorry. Are you seeing my slides? Because it tells me that it's paused.
We saw your slides and I think you were writing, but we were not seeing your writing. And now we just see you, which is lovely.
Okay, so I think I must have clicked something. Okay.
Here we go. Good.
Okay, good. Sorry. So for a weakly coupled system, interactions are collisions. So collisions of the microscopic particle constituents. So the idea is that you have a particle constituent that is going along its merry way until at some point it meets another particle constituent. They undergo a collision and then out come some other particles. And that, of course, will change the phase space density of the particle because collisions will transfer momentum and energy among the different particles. I mean, if you can think of billiard balls, you see a billiard ball going into another billiard ball, then out come the two billiard balls going out with different energies and momentum. So now we can start to see what the fine print of the Boltzmann equation can be. So this kinetic approach can be valid if the mean free time, so the time this particle will propagate before it undergoes a collision or between each collision, on average, of course, is much longer than the duration of the individual collision. Because I have a collision, then I go my merry way for a while, and then I experience another collision. And even if collisions are not instantaneous, they last much longer than the mean free time between each of them, so that I can treat each collision as a separate event. If instead the duration of each collision becomes comparable with the mean free time or with the wavelength of the constituents, then the system is no longer weakly coupled, because I now cannot think of particles propagating and undergoing rare collisions, but my system is really, I can no longer really describe my system in terms of microscopic particle constituents. The system is becoming something strongly coupled, like, for instance, a liquid, which undergoes constant interactions, which cannot be described by this propagation, then collision, then propagation, then collision, and so on. And so at first order, then we can expect elastic collision. So here, for instance, I have a gluon coming in, a gluon coming in, and a gluon coming out, and a gluon coming out. You can have the same with quarks, or quark coming in, gluon coming in, quark coming out, gluon coming out, and so on. And in general, though there are some caveats, which I might try to discuss if I have some time. So here I have binary collisions, but you can also have, I don't know, 2 particles coming in, 3 coming out, or so, and so on. They will be suppressed for a weakly coupled system, because the idea behind that is that this is where my expansion parameter comes in. So because the idea, and you will see that when you do quantum mechanics and quantum field theory, is that for each extra particle I will add to my collision, I pay the price of an extra power of my expansion parameter. So for QED, we said it's 137, and for QCD, it could be 0.3. So in the case of an electromagnetic plasma, I pay a really big price for each extra particle, so that's a well-behaved expansion. In the case of QCD, the price I pay might not be that big, so one might wonder if and how much this formalism will be applicable, which is something that I will touch more in the second talk. So now, in the few minutes that I have remaining, let me try to wrap up and say, what is the form of this term mathematically that describes interaction? So when you have 2-to-2 collisions, so this is my left-hand side, and the right-hand side has this form, which might look a bit puzzling. So let's try to unpack it. So I have something here, which is the phase space integral with energy momentum conservation. It means that I'm following the phase space density with momentum p, and I'm integrating over the phase spaces of the other 3 momenta in my process. So that means that this particle can come in with any momentum, this particle can go out with any momentum, and this particle can go out with any momentum. But of course, they have to satisfy the fact that energy and momenta are conserved, so they cannot do whatever they please. They always have to come out such that p plus p prime is equal to k plus k prime for the momenta, and the EP and the incoming energies have to equal the outgoing energy. So the phase space is not as big as it might look like because of that. Then what is this quantity here is the quantum mechanical probability of the interaction. So what's the probability of having a gluon with momentum p and a gluon with momentum p prime going in, and a gluon of momentum k and a gluon of momentum k prime going out? So this is something that you can compute in quantum mechanics or in quantum field theory. And finally, there's the last line. So what is this? So fk prime is a compact notation for fk, x, t, and so on. So in this case, so this is what is called the gain term. So it corresponds to the red arrow, so going from right to left. It means that the reaction is going in this way. So I have a particle coming in with momentum k, another coming in with momentum k prime, and then going out with momentum p and going out with momentum p prime. So these factors of 1 plus f for boson is the so-called Bose stimulation factor. If you had fermions, you would have 1 minus F. It corresponds to describing the fact that bosons want to be where other bosons are. So this is the stimulation factor that also explains, this is also related to how the laser works. Whereas with the minus sign, you are implementing the Pauli exclusion principle, which tells you that you cannot put a fermion in the same quantum state as another fermion. So this is the gain term. So you see that this term will be positive because here you have, as you start from an initial state that doesn't have your momentum P, and you gain a final state with the momentum P, so that will increase your F of P. And then you have the negative contribution here in the loss term. So in the loss term, things are going this way. So you have your particle with the momentum P coming in and absorbing a particle with momentum P prime, and then this depletes the modes with momentum P. So, and this is an exercise that I will leave it to you. If you couple the explicit form of the Bose-Einstein distribution with energy conservation, you will see that this combination here vanishes. So this means that equilibrium is a steady state of this equation, which means that when you're in equilibrium, there's as much reactions going from left to right than reactions going from right to left. And which means that once your evolution has approached the thermal equilibrium state, it will stop because the right-hand side of the equation will be 0 and the time evolution will stop there. So this has brought us from a magical Gedanken ideal gas, which is just prepared in a state of thermal equilibrium and just stays there because there are no interactions, to a realistic system where equilibrium is something that is self-sustained. So even when you are in equilibrium, your particles are still undergoing lots of interactions, but the net effect of these interactions is 0. Before they are in equilibrium, either the gain term is larger than the loss term or the loss term is larger than the gain term. And so there is a net effect and your distribution evolves towards equilibrium. So before I conclude, let me just say 2 more things. I don't want you to walk away thinking that QCD is just this collision of billiard balls, because this is what it might look like. So I have my billiard ball coming in and interacting with another billiard ball, and then I have my 2 billiard balls going out. It's a bit more than that. You can have these more complicated processes. And without going into the detail, I will do that next Friday of what happens in this blob. In QCD, you also have these processes where 1 billiard ball comes in and 2 billiard ball goes out, which is something that I've never seen happen in billiards. And, or vice versa. I've also never seen 2 billiard ball come in and 1 billiard ball go out. And these processes are very important for thermalization because they change particle number. So they're very effective at chemical equilibration. And they also rapidly transfer energy either up or down. So if it's going this way, it's rapid at moving energy from the ultraviolet to the infrared. If the reaction is more going that way, it's efficient at moving energy from the infrared to the ultraviolet. And so as a teaser for the next talk, I just show here some results that are obtained by solving the kinetic theory for QCD plasma. So these are results from Søren Schlichting and Xiaoyan Du. So this is the distribution of gluons. So you can see in red here, this is in this case, they chose an initial condition which has a peak at an energy that's much larger than the final temperature that is reached at the end of evolution. And then you look at, this is how the distribution function looks like after some time, at a later time, at an even later time, and at an even later time, it's almost at the equilibrium distribution, and then it eventually approaches the equilibrium distribution. So this is how the Bose-Einstein distribution looks like on a log-log plot. And in their system, they also quarks. Initially, their quarks were 0, but they later start to be formed, and then again they reach a Fermi-Dirac distribution, which looks like this in a log-log plot. And this is instead results by my collaborators and myself, where the left-hand side looks just like what Søren did, and the right-hand side, we also look at an overoccupied initial condition. So our initial condition is instead most of the particles and most of the energy is now in the infrared, and the ultraviolet is depleted. And you see that as time goes by, the infrared moves down and the ultraviolet moves up, and you approach equilibrium. And here I plot the same distribution function, but multiplied by the cube of the momentum, so that the area under these curves is directly proportional to the energy density. So you see how in this case, initially, essentially all of the energy was in the far ultraviolet, and now the energy is being transferred more and more towards the thermal range. Whereas in the opposite case, initially the energy was all in the infrared, and as time goes by, it shifts towards the thermal regime. So this is what I will explain next week, is an energy cascade. And with that, I can come to my summary, in which under the assumption of weak coupling, and I try to stretch that conditions apply, and that I will explain better what are these conditions next Friday. A thermalization process that describes how we transition from nuclei to near thermal quark-gluon plasma can be described by kinetic theory. Thank you.
Okay, super. Thank you. That was a very, very nice introduction. Do we have questions from the audience? Yes.
So earlier you showed a plot about the anisotropy predictions and how for hydrodynamics to work for that you have to input like a turn on time, right? And that was kind of like fitted almost. That seemed like a kind of a knob that you can turn to fit to the data. It kind of seems like from this process that you're describing that maybe you could have a prediction for that turn on time. Is that something that's like possible, or am I
Yes, so there are predictions for this turn on time, or for this thermalization or hydrodynamization time from theory. So in the next talk, I will maybe try to give an overview at the beginning. So in the case of the weakly coupled methods I've been describing, even though they require couplings in principle, which are smaller than those that we find in these real life conditions, we can first set up the theory with small couplings and then extrapolate to these larger couplings and see what happens. And if you try this game, you get times that are in this ballpark. So in the specific case of this plot, this is a proton nucleus collision. So the time here is small, also is small because also the system is small. For a nucleus-nucleus collision, you would expect a larger time, a larger fraction of a Fermi, well, or of a Fermi over C, if you want to be precise. And you can get times that are of this order of magnitude also from weakly coupled methods.
Yeah, thanks. Why would you expect a different thermalization time for AA versus PA, in the sense that for both, well, certainly for the AA system, if it's 0.4 Fermis, light hasn't had enough time to cross the entire system, so it's local thermal equilibrium time.
Right.
Yeah. So how does the global size affect the local thermal equilibration time?
Yeah. Okay. Good question. I don't know indeed if maybe I said that, but maybe I wasn't right. If you really should expect this system size dependence for the key thermalization times. That's a good point. I should think more about it. Yes.
Super. Other questions? Yeah, please go ahead.
I think very early on slides, when you were, I think, doing a classical approximation of the energy density of the QGP, I believe it was QGP.
This one.
Yeah, this one. In the non-interacting limit. You seem to have made the assumption that you model it as a black body. Why is that sort of a valid assumption?
Well, that is, so that really, that vertical line here, sorry, horizontal. That horizontal line here is really this quantity here. So it's, this black body is really this, calculation here. So it's assuming that your quark-gluon plasma is just made by quarks, massless quarks, and gluons that are non-interacting. And in this case, the energy density is given exactly by this. And so it has this Stefan-Boltzmann form. So here the Stefan-Boltzmann limit for photons is just this times 2, because there are only 2 photons and there are 16 gluons. And here I have 16 gluons plus the fermions. But these are just the details of the microscopic constituents of the plasma. But for any plasma of ultrarelativistic fermions or bosons, the energy density and the pressure are T⁴ times a constant that you can compute by these relatively simple integrals of the Bose and Fermi distribution. And that's called the Stefan-Boltzmann limit. Now, the good question is, why does it work so surprisingly well to a first approximation? Let me stay where I was. I shouldn't have gone. Because here, I mean, between the results with no interactions at all and the actual calculation that exactly solves, well, that solves the discretized quantum common-dynamics equations on a computer, and with full accounting of the interactions, you only have a 20% difference. So in the case of thermodynamics, interactions aren't really that important. You also have another example if you want. In, from ADS CFT that I've discussed before here, you have this n=4 theory, which you can solve. I mean, if you take it at 0 coupling, then the energy density of the n=4 theory will be given by a formula like that, where you have to adjust these constants for the right numbers of gauge boson scalars and quarks that you have in that theory. And that would be the energy density at 0 interaction. And then with the ADS correspondence, you can also solve the theory essentially exactly at infinite interaction. And you find that in this case, the result for the pressure and energy density and so on, they are at 0.75. They're 3/4 of the non-interacting result. So going within that theory, going from 0 interaction to going to infinitely strong interaction only changes things by 25%, probably because thermodynamics isn't really so sensitive to the strength of the interactions. Conversely, of course, thermalization is enormously sensitive to the strength of the interaction. So if you have no interactions at all, you will never thermalize. And if you have very strong interactions, you will thermalize very fast. So that would be a very different case.
Thank you.
Do you think, this difference between 0 interactions and infinite interactions, that it's so small that there's something intimately wrapped up about the system being ultra-relativistic?
Good question. So, do you know of any relativistic or non-relativistic strongly coupled systems? Well, I guess yes, water, for instance, again. But so, well, of course, in a non-relativistic system, the energy density is essentially the mass density. But what about the pressure? So, good question. I don't know.
Yeah, me neither. Okay, super. Other question?
Yeah, so in the picture you just showed, there was a mu b equals 0.
Yes, this is at mu b equals 0. Yes.
So is this why this choice?
So why this choice? I guess for two reasons. One reason is that so mu b is the baryon chemical potential, so the chemical potential that's associated with baryon number. In a heavy ion collision, baryon number is not 0 because we have 200 baryons on one side and 200 baryons on the other side. So baryon number is maybe 400 for very central, but the chemical potential will be very small compared to the temperature for the very central high energy collisions, simply because you put in a lot more to the energy density than there's a lot more quarks and gluons essentially that are just created by the interactions that the sort of valence quarks that come in from the baryons on either side. So mu b equals 0 is a good choice if you want to describe ultra-relativistic heavy ion collisions at high energy. If you want to look for the critical point, it's not a good choice, of course, but for LHC physics, it is a good choice. And also it's a practical choice because you want to, in this case, you want to do a comparison with lattice data. And as soon as you try mu b larger than 0 on the lattice, so this discretization of the QCD equations, there's no problem with the discretization itself, but the problem is then putting them on the computer, because once you put a non-zero chemical potential, you start to get imaginary parts in your equation, which introduce oscillations, and then it becomes numerically horrible to do on a computer. So there are some lattice results at finite but small values of mu, but it's still impossible to explore the full phase diagram of QCD, which is a phase diagram in the T and mu b plane on the lattice.
So, okay, thank you. So is this something you also assume in your kinetic theory calculations?
No. So in the kinetic theory, we can. So for instance, in this paper by which I have quoted at the end, so in here they actually look at the kinetic theory, where they really follow separately the distribution of the gluons, of the quarks, and of the anti-quarks. So they don't assume that the distributions of quarks and anti-quarks are the same, which would be the assumptions to do if you're at 0 chemical potential. They also solve for the possibility of a non-zero chemical potential, which means that the distributions of quarks and anti-quarks are different. So no, in the kinetic theory, we're not limited to that. In what I will show next week, it will even be simpler because there will not be quarks at all. And so the problem will not be applicable, but people have done it, yes.
So what? So the quarks go into equilibrium just separately from the.
So you can, for instance, so if you start with a system which has an equal number of quarks and anti-quarks, it will of course stay for equal numbers of quarks and anti-quarks because of the various symmetries of the theory, like charge conservation and so on, and baryon number conservation. But if you start with a system which has more quarks and anti-quarks, or where then this will be conserved and the quark and anti-quark distribution will evolve differently from each other. And they will eventually reach thermal equilibrium with the Fermi-Dirac distribution with the non-zero value of the chemical potential, which corresponds to the baryon number that was present initially.
Do you want to follow up with anything?
No. Do you want to say something?
Okay, cool. Any last question? Super, Jacopo, thank you so much. That was really great.
Thank you. It's been a pleasure, and looking forward to next Friday.
Yeah, so looking forward to hearing from you next week.
Yeah, I will send you the abstract soon, or Monday at the latest.
Perfect.
Bye.